So how does a machine actually learn? Well, usually it looks at a bunch of examples you give it and tries its best to find a pattern. But what happens when those examples aren't perfect? When the real world gets a little messy. It turns out how a model handles that messiness is pretty much the difference between a fragile algorithm and a truly robust one. Today, we're going to dive into a really powerful idea that kind of rethinks learning from the ground up. Okay, so to really get this new idea, we first have to talk about the classic approach. This is the default way most machine learning has been done for decades. It's called Empirical Risk Minimization, or ERM for short. The logic behind ERM is, super simple. Your goal is to make the fewest mistakes possible on the data you have right in front of you. The algorithm treats every single data point like it's an infinitely precise, perfect piece of information. The mission? Find a rule that fits these exact points the best. Seems totally logical, right? But that core assumption of perfection, well, that's its greatest weakness. So, in a perfect world, ERM works beautifully. You've got your blue dots, you've got your orange dots, and the algorithm just draws a clean, simple line right between them. Everybody's happy. This is the textbook case, the ideal scenario. But we all know the real world is never this clean. Data has noise. A sensor might glitch. Somebody makes a typo. It happens. So what happens when just one data point is slightly out of place? Just one little orange dot on the wrong side of the tracks. Because RMET treats every single point as the absolute truth, it will literally bend over backwards to correctly classify that one noisy point. Suddenly, our simple, elegant line is gone, and it's replaced by this complex, twisted boundary. This is a classic case of what we call overfitting, and it's a total disaster. Sure, this new model might be perfect for the training data, but it's going to be terrible at classifying any new data it hasn't seen before. And this brings us to the big question. If trusting individual data points so completely just makes our models brittle and fragile, what's the alternative? How can we learn from data without becoming a slave to all of its little imperfections? And that leads us to the core concept of this amazing research, Vicinal Risk Minimization, or VRM. Now, the name sounds pretty complex, I get it, but the idea itself is beautifully intuitive. It's all about looking beyond the single point and seeing the entire neighborhood around it. So here's the crucial difference. ERM sees each example as a sharp, tiny pinprick of truth. Think of it like a single, perfect coordinate on a map. VRM, on the other hand, says, hold on, that data point is probably not the only possibility. The truth is likely somewhere in the vicinity of that point. So it treats each example as the center of a small, blurry cloud of possibilities. So, to put it a bit more formally, Vicinal risk minimization doesn't try to get the error to zero on the exact points you gave it. Instead, it tries to minimize the average error over a small region, a vicinity, around each of those points. It's basically learning from a slightly blurred version of reality, which, it turns out, makes it so much more robust to noise and all those imperfections. Okay, let's peek under the hood at the engine driving this idea. This equation here defines the vicinal risk, which is just the total error our model is trying to crush. The key difference from the old way is this integral sign. Instead of just calculating the error, or loss, L, for a single point xi, we're now averaging that loss over a whole distribution of points pxi around it. In simple terms, that integral is the mathematical magic that turns a single point into one of those blurry clouds, forcing the model to be tough against small wiggles in the data. All right, now this is where things get really wild. Vicinal risk minimization isn't just some neat new trick. The authors of the paper show that this single principle is actually the secret, unifying framework behind a ton of famous, seemingly unrelated machine learning algorithms. So let's start with a true classic, ridge regression. It's a fundamental technique, been around for ages, used to stop overfitting in linear models by adding this little penalty term to the cost function. So check this out. The paper shows that if you take the VRM principle and apply it to a simple linear model, and you define your vicinity as a simple spherical cloud, a Gaussian kernel, the math just works out. And what pops out the other side is the exact formula for ridge regression. That penalty term that engineers were adding for years just because it worked, it wasn't just a good hack, it was an implicit way of considering the neighborhood of the data all along. Mind-blowing, right? Now, let's see how this builds. What if the vicinity isn't just a simple circle? For example, when you're recognizing an image of the number 7, you and I know that a slightly rotated or shifted version is still a 7. Well, VRM can handle this. You just shape the vicinity to represent those kinds of transformations. And this is the core idea behind really powerful algorithms like tangent prop, which build these real-world invariances directly into the learning process. And now, for the biggest connection of all, support vector machines. I mean, SVMs are one of the most powerful and celebrated classifiers in all of machine learning. They're famous for finding the absolute best line to separate data, focusing only on the points closest to that boundary. And here is the punchline. The paper shows that a classifier built on the VRM principle, like this logistic classifier they mention, it naturally acts like a flexible soft margin classifier. But here's the kicker. As you shrink the size of that vicinity, making those blurry clouds smaller and smaller until they're basically zero, its decision boundary converges and becomes the exact same boundary as the classic, rigid, hard margin SVM. Suddenly, it all connects. ERM is one extreme, the classic SVM is the other, and VRM is the general principle that beautifully unifies them both. But VRM isn't just about explaining the algorithms of the past. It's about building the algorithms of the future. By making this idea of a vicinity something we can actually control, we can create brand new, more powerful approaches. A really key innovation is realizing that the vicinity cloud shouldn't be the same size everywhere. Think about it. Where you have very little data, you're less certain, so you should probably use a bigger, blurrier cloud. But where the data is super dense and you have more confidence, you can use a smaller, sharper cloud. This is adaptive learning, and it's a huge step forward. So, the big question, does it actually work? Oh yeah, absolutely. On this Wisconsin breast cancer dataset, you can see that the adaptive VRM consistently gets a lower test error than a standard hard SVM. And just look at the difference when the training set is tiny. With only 10 examples, the improvement is really significant. This shows that VRM is especially powerful when data is scarce. And we see the exact same story on the classic MNST dataset of handwritten digits. In the task of separating the digit 1 from all the others, the adaptive VRM method again outperforms the standard SVM, and it does it across different training set sizes. This proves it's not a fluke, it's just a fundamentally more robust way to learn. And this might be the most powerful part. The whole VRM framework naturally extends to learning from unlabeled data. You can basically tell the model, hey, I don't know the label for this point, but I know it's a real data point. So whatever decision boundary you draw, it probably shouldn't pass too close to its vicinity. This simple idea lets the model learn the underlying structure of all your data, improving its accuracy even when you have very few labels. It's a game changer. So, after seeing the theory, the connections to old algorithms, and these brand new results, what's the big lesson? What's the main takeaway from all this? Let's just recap the journey real quick. We started with the classic approach, ERM, and saw that it's fragile because it treats every single data point as perfect. Then we saw how Vicinal Risk Minimization completely fixes this by learning from those blurry clouds instead of sharp points. We discovered this isn't just a new trick, but a grand unifying theory that connects giants like Ridge Regression and SVMs. And maybe most importantly, we saw how this principle gives us a direct path to creating new adaptive algorithms that just perform better in the messy real world. You know, the core idea here is really about questioning our assumptions of perfection. VRM became powerful by asking a simple question: what if the data point isn't exactly right? And that leads to a final thought I want to leave you with. What other foundational assumptions are we making in artificial intelligence? What other perfect points are we trusting way too much? And what incredible new breakthroughs are just waiting for us when we finally start to embrace the vicinity?